This meeting is being recorded.
Hello. In the last class, I have started discussing cryogenic distillation. There, I have discussed how the number of equilibrium stages or number of ideal trays are determined using McKeithly method for cryogenic distillation process. So it was basically based on graphical methods, though some analytical techniques are also there. Graphically, we use equilibrium curve and operating lines. Operating lines for rectification section, operating lines for the stripping section. These two I already discussed. So remaining one is the operating line for the feed conditions or Q lines. That will be discussed and up to the plate calculation. So this is one typical photograph of overall distillation column. So based on this, here you can see that feed mixture is entering here. We are having condenser here, a reboiler here, and bottom products and top product. So based on this, we will be uh, doing material balance for the feed trays and of course overall distillation column. That material balance will also be taken under consideration for finding out the operating lines. So for doing material balance for complete fractionating column, a quantity Q is defined, and it is defined as the number of moles of saturated liquid produced on the feed plate by each mole of feed added to the column, and is used to reflect the quality of the entering feed stream. Uh, uh, we can also define Q. This is the definition. Actually, by this way, we can directly determine how much liquid and how much vapor is there in the feed. Quantitatively, Q is defined as this. Q is equals to heat needed to vaporize 1 mole of feed at entering conditions by molar latent heat of vaporization of the feed. And if we write or express this in terms of enthalpy, then it is equals to HV minus HF divided by HV minus HL, where HV is the enthalpy for the saturated vapor. This is enthalpy of the feed. This is enthalpy of the saturated vapor again, and HL is the enthalpy of the saturated liquid. So utilizing this definition of Q, we can have this relation L bar, that is liquid flow rate in the stripping section, that is equals to L liquid flow rate in the rectification section plus the liquid fraction that is coming from the feed, that is Q multiplied by F. So this will give the liquid flow rate in the stripping section. Whereas vapor flow rate in the rectification section, that will be equals to V bar, that is vapor flow rate, which is entering into the rectification section from stripping section, plus the vapor fraction that is coming from the feed. That is 1 is the total fraction, 1 minus Q is the fraction remaining for the vapor portion multiplied by F. So using this, ultimately we are getting this expression. So for getting this expression, of course, overall material balance for the total distillation column, that also has to be taken care of. And after elimination of uh, F, B, and D, we'll be getting Y is equals to Q by Q minus 1 into X uh, minus xf by q minus 1. Here for a particular distillation operation, q by q minus 1 is constant, and this is also constant, xf by q minus 1. So that means this equation is of the form of y equals to mx minus c. So this will give a straight line with a slope of q by q minus 1 is known as the Q or feed conditions line. Its intersection with XY diagonal line occurs at x equals to xf, where xf denotes the overall mole fraction of the more volatile component in the feed. So from this feed line will start. Now for different feed condition, let us see what is the value of Q, and for that what is the slope of the Q line. Now for subcooled liquid means liquid below its boiling point. That is subcooled liquid. So there Q value will be definitely greater than 1, because there we need to supply heat to convert 1 mole of feed into saturated vapor. So first portion is sensible heat, then it will come to boiling point, then we have to supply latent heat of evaporation to convert it into saturated vapor. So definitely Q is greater than 1. And now if you substitute in this slope expression, then we will get Q slope will be greater than 1. So this feed line or Q lines will be lying in the first quadrant, in between diagonal line and equilibrium curve. Now for the saturated liquid feed, Q value is equals to 1, because at that time if we just supply latent heat of preparation, it will be converted to saturated vapor. So Q definition will be lambda by lambda, that is equals to 1. So if Q equals to 1, then slope will be 1 by 1 minus 1, that is 1 by 0. Something divided by 0 is infinity, so slope of this line will be infinity. That means it will be a vertical line. So feed conditions line will be vertical. Now let us discuss this one, saturated vapor. If feed is saturated vapor, then as it is already saturated vapor, then we need to supply 0 amount of heat to convert into convert the feed into saturated vapor. So that means Q value is 0 by lambda, that is 0. If Q is equals to 0, then Q by Q minus 1, that is 0 by anything is 0. So that means slope is 0. It should be horizontal line. So for saturated vapor condition, feed conditions line is horizontal lines. And if it is superheated vapor, then we need to subtract some heat to convert it to saturated vapor. So Q value is less than 0, and in that case slope will be within 0 to minus 1. So it will be a straight line lying into third quadrant. Whereas if the feed is mixture of liquid and vapor, in that case, Q line will be in between. Q value is 0, from 0 to 1, and it is negative. So it will be lying, this line will be lying in the second quadrant. So let us see that Q lines or feed conditions line for different condition. So this one is for subcooled liquid, this is for saturated liquid, this is for liquid vapor mixture, this is for saturated vapor, and this one is for superheated vapor. Now, based on these feed conditions, if we draw Q line or feed line starting from this point except, then this Q line or feed line will be intersecting with the operating line for the rectification section. As this point of intersection will be lying on the feed tray, and this stripping line will be ending over there, then we already got another point on the stripping operating line. So for drawing stripping operating line, we need not determine either slope or the intercept. We can directly find out this point of intersection and XB point and join these 2 points by straight line. That will be the operating line of the stripping section. So now if we want to determine um, number of uh, um, equilibrium stages in this distillation column, then we can just start drawing staircase like things like this. That means from this point we have to draw horizontal line up to the equilibrium curve. We will get point 1. From there, we have to draw vertical line up to operating line for the rectification section. We will get this point. So, as we are just completing this one step, that will be equivalent to one equilibrium stage. And this vertical line, we can just count the vertical line drawn. By doing so, that will give you the number of equilibrium stages in the distillation column. Now, why we are doing this, that means drawing a horizontal line up to equilibrium curve and then vertical line up to operating line, that I will be discussing later on. So for the time being, this is the process to determine number of equilibrium stages in the distillation column. So let us discuss how we will be constructing this. This is step 1. First of all, plot equilibrium curve and 45-degree lines, that is diagonal lines. So this is equilibrium curve and this one is the diagonal line. Then plot given composition points, that is feed point, bottom products points and distillate point. So distillate point, feed point and bottom products point. This should be located. Third, draw Q lines from point except. So based on the feed condition, we can draw this feed line or Q line. So here feed lines, feed condition is vapor liquid mixture. So feed line, Q line will be like this. Now we need to determine R minimum. R minimum, actually if we need to determine reflux ratio, and based on that if we need to design the distillation column, then we must determine R minimum, and this R minimum we will be able to determine if we find out point of intersection of this feed line with the equilibrium curve. So where it will be intersecting with the equilibrium curve, that point we should determine, and we need to draw another line starting from XD points to up to that point, and slope from the slope of that operating line or intercept of that operating line, we can determine R minimum. So as soon as we are getting R minimum value, then actual R, reflux ratio, uh, 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 we need to consider uh, any value in between this. That means we have to multiply R minimum by 1.05 to 1.15. Any value we have to take in between this and multiply R minimum by that to get R value, actual. This is value is taken for cryogenic distillation. For chemical distillation, we generally take this factor as 1.3 to 1.5. So now step 7, or rather step 6, draw operating line for the rectification section. As soon as we got the actual reflux ratio, we need to draw this operating line where these two lines, operating line for the rectification section and operating lines for the feed conditions, they will be intersecting at this point. So as soon as we are getting this point and this XB point joined by a straight line, and that will be the operating line for the stripping section. Now for number of equilibrium stage determination, this is step 1 from XT, locate X1 and Y1, drawing a horizontal line to the equilibrium conditions for stage 1. Then step 2, find Y2, drawing a vertical line to the rectifying operating lines. Locate the mass balance conditions between X1 and Y2. Step 3, from Y2, draw a horizontal line to the equilibrium condition for stage 2 to locate X2. And next is return to step 2 and cycle through uh, step 2 and 3 until xi is less than xf. Draw subsequent vertical lines to the stripping section and continue. Step 5, end after when xi is less than xp. There we should end. So in this way, total number of vertical lines we have drawn will give you number of ideal stages in this distillation column. So here again another uh, uh, graphics have been shown, uh, just showing all the lines, that is equilibrium curve, diagonal line, operating lines for the rectification section, Q line, and operating line for the stripping section. And then number of stages with along with composition. That steps have been shown here. So this is just repetition, but in details we will be getting composition of liquid and vapor in each trace. And as I discussed, to determine the minimum reflux ratio, what we need to do, that I have shown here, that Q line is drawn up to the equilibrium curve where it is intersected. So at that condition, the reflux ratio of this operating line will be the minimum reflux ratio. So by returning no existing vapor as reflux or no existing liquid as boil up, the operating line's intersection is as far to the left as equilibrium allows. It cannot go beyond this equilibrium curve. So although this is the minimum amount of reflux, it takes infinite stages. Note the pinch point between the operating lines and equilibrium curve. So here the tower height will be infinite. So this is not practical. Similarly, for determining minimum number of stages for McKinley method, so this is other extreme, total reflux. So if we gradually increase the reflux ratio, ultimately this operating line will be moving towards the diagonal line and coinciding with the diagonal line. So all the operating lines, stripping line, operating line, rectifying operating line, they will be merging with the diagonal line. So at that condition, if we determine number of equilibrium stages, then that will give you the minimum number of equilibrium stages or minimum number of ideal trays in the distillation columns by returning all the existing vapor as reflux and all the existing liquid as boil up, the operating lines have slope of 1. That means they will be lying with this diagonal line. All this is the minimum number of stages. No product is produced. Note the feed must then go to 0. Now, this is very important points to remember, that is limiting reflux conditions and optimum reflux ratio. It is apparent that there must be a compromise between two limiting conditions of reflux. Total reflux involves too large an expenditure in energy cost for the required refrigeration, while minimum reflux involves too large an expenditure for the separation unit. In typical distillation columns used in chemical process industries, the optimum reflux ratio presently lies somewhere between 1.15 and 1.35 times the minimum reflux ratio. This is a change from earlier ratios of 1.2 to 1.5, which were the norms before the escalation in energy price. For cryogenic separation systems, the optimum reflux ratio is more often in the range of 1.05 to 1.15 times the minimum reflux ratio because of the increased refrigeration cost associated with such uh, conditions. So now in summary, uh, let us repeat what we have discussed in this lecture. Cryogenic distillation for oxygen and nitrogen separation from air was discussed. A typical double column binary distillation configuration was demonstrated in part 1. Definitions of constant molar overflow, Q parameter, reflux ratio, total reflux, minimum reflux, and optimum reflux ratio were also given with explanation. Differences between equilibrium curve and operating lines and their interconnectivity for determining number of stages were explained. The equilibrium curve, diagonal lines, and operating lines were plotted. Stepping through stages to show the change in composition in different stages of the column was also described. Next lecture will continue our discussions of binary distillation of air separation using McKinley method with a design problem. So with that, let me conclude my discussions. Thank you.